So last time we talked about valence bond theory, but the valence bond theory that we've gone over so far does not explain how we would end up with a tetrahedral shape. So we're going to go over the concept of hybridization in this presentation. Our objectives will explain the concept of atomic orbital hybridization. We'll determine hybrid orbitals associated with various molecular geometries. Valence bond theory predicts that if you put a water molecule together, it would end up with overlapping s orbitals from hydrogen and p orbitals from oxygen. The p orbitals are all perpendicular to each other via our understanding of electron orbitals. So when we form bonds, we would have a 90-degree angle. But we know this is not what happens. Experimental evidence tells us that the prediction from VSEPR is much closer to the truth, and the bond angle is instead 104.5 degrees. So how can we make this work? We extend the theory to include a new idea. That idea is hybridization. Wave functions of atomic orbitals combine using a mathematical technique called linear combination of atomic orbitals. For those of you who have an interest in mathematics, this refers to using linear algebra to solve wave functions. Computers are good at that. We use computers for these types of calculations. Combined orbitals have new shapes and are called hybrid orbitals. Where do these come from? Well, we combine 2 electrons in the 2s orbital and 2 electrons from the 2p orbital to form our oxygen atom. So we put it into a bond. Right? So instead of having this picture where we've got things at 90 degrees, we now have our new bond angle, which is closer to the actual measured 104.5. Hybridization runs on these basic assumptions. 1, hybrid orbitals form in covalently bound atoms. So we're talking about covalent bonds. 1 electron is coming from one species, 1 electron is coming from the other. Hybrid orbitals have different shapes and configurations than atomic orbitals in isolated atoms. So they're not going to look the same that they did before. All that stuff that we studied about S and P and the nodes and all that, not going to be the same for hybrid orbitals. Hybrid orbitals are created by combining atomic orbitals, and the number of hybrid orbitals created in the set of hybrid orbitals is equal to the number of atomic orbitals that were combined to make that set. All hybrid orbitals have equivalent shape and energy. The type of hybrid orbitals in the molecule depend on electron geometry predicted by VSEPR. And finally, hybrid orbitals overlap to form sigma bonds, and unhybridized orbitals form pi bonds. So if we recall, sigma bonds were where we had our electrons overlapping along the axis, and pi bonds were where we had it overlapping like above and below the bonding axis. So when you have a linear electron geometry, you have 2 sigma bonds. Note, I will be omitting the term electron in front of geometry in succeeding slides, but it will be implied henceforth. Anyway, there are 2 bonds, and we need to hybridize them. We'll combine an s and a p orbital to make an sp orbital, which has 1 skinny side and 1 extra long side. So that is this guy. When you put those 2 together, they line up to be 180 degrees apart, which is what our VSEPR predicts. Okay, so it's still kind of like a figure 8, but it's distorted so that one side is really, really fat. Now, this is not the full story. We can also draw an electron diagram, including the energy level of the orbitals in question, and the combined orbital has an energy between the s orbital and the p orbital. Okay, so we start with unhybridized orbitals on the left here, we have both of our electrons in the 2s, and then we combine it with a p orbital and we make an sp. Both of them have one electron and they're both spin up. That is on purpose. The p orbitals that are not hybridized will stay at the energy level they were at previously. Okay, so in particular, this example that they gave was for beryllium chloride, but you could imagine a bunch of linear things that would follow the same general pattern. CO2 would have electrons in the p because we have pi bonding there. Let's move on to sp2. Okay, when you have trigonal planar geometry, you have 3 sigma bonds. There are 3 bonds, so we need to hybridize 3 orbitals. We combine an s and 2 p orbitals to make sp2. Note that the names are going to follow a pattern. We indicate which orbitals and how many by using the superscripts. And when we use more than one of a certain type, we label it. In this case, 1s and 2p, which is designated as p or sp raised to the second. Okay. The sp2 orbitals also have one skinny side and one extra large side in the general p orbital shape, but in this case it is not aligned along any Cartesian axis perfectly. It's in between. And when we line them all up together, they have a bond angle of 120 degrees, which is the trigonal planar arrangement. Our electron geometry, our electron diagram rather, indicates the energy level of the orbitals in question. The combined orbital will have an energy in between the s and the p, or the p orbitals that it's made from. The p orbitals that we did not hybridize, again, the 1 in this case, stays the same. This time we took electrons and distributed them across 3 sp2 orbitals. Spin up when we are done. All right, when you have an electron geometry that is tetrahedral, you have 4 sigma bonds. So we need all 3 of those p orbitals, and it will be sp3 for our hybridization. Again, we end up with a skinny side and an extra large side, and the general p orbital shape. And again, it's not aligned along any Cartesian axis. When we put it all together, the bond angle is 109.45 degrees in a tetrahedral shape. Our electron geometry, our electron diagrams show that when it's hybridized, all 4 have the same energy. And it's between the energy of the s and p orbitals that they came from. And again, we have 1 electron in each orbital. When you have trigonal bipyramidal electron geometry, you have 5 sigma bonds. There are 5 bonds, so we need to hybridize 5 orbitals. We'll combine an s, all 3 p orbitals, and 1 d orbital to make the sp3d orbitals. The sp3d orbitals also have 1 skinny small side and 1 extra large side in the general p shape. 2 of them align along an axis and 3 are off axis. The ones that align along an axis are said to be in axial positions, and the ones that are not aligned are in equatorial positions. As you recall from VSEPR, the bond angle between axial and equatorial positions is 90 degrees, and the bond angle between the 2 equatorial positions is 120 degrees. This forms the trigonal bipyramidal shape. Our electron diagrams show that when hybridized, all 5 have the same energy between the energy of the sp and d orbitals that they came from. But we didn't have any electrons in the d orbital to begin with, so how is it we have 1 each in the hybridized version? Now, there are different schools of thought on this. There is no definitive answer, so just start with the left and make the picture on the right. Now, I will pause here and say that if we have a lone pair, then we would in fact have an up and a down electron in our hybridized orbital. This is a representation of not having that lone pair. And that goes for everything that we've done so far. So if we have a lone pair, we hybridize and we put 2 electrons into that orbital. I will give you an example of it later. All right, what about the octahedral geometry where we have 6 sigma bonds? The 6 bonds mean that we need to hybridize 6 orbitals. So we'll combine an s, all 3 p, and 2 d orbitals to make sp3d2 orbitals. The sp3d2 orbitals have one skinny side and one extra large side, just like everything else, general shape of the p orbital. And they align along all the Cartesian axes with 90-degree angles between everything because they're aligned on a Cartesian plane. So that is how we form our octahedral shape. Let's try hybridizing something. Draw the hybridization electron orbital diagram for carbon in sp2 configuration. So in this case, we start with the valence shells of carbon in the ground state. There are 2 electrons in the s and 2 in the 2p. 2 scenarios are possible. In one, we have 3 sigma bonds and 1 pi bond, and in the other, we have a lone pair and 2 sigma bonds. In the first case, once we hybridize, the orbitals will each have 1 electron, each of the sp2s and in the 2p that is remaining. And they're all spin up. Why are we only putting 1 electron in each of these boxes? Because the other electron is coming from the other atom in the covalent bond. All right, in the second case, there would be 2 electrons in our first hybridized box and no electrons in the 2p, and then we have the 2 singles for where we're bonding covalently. Okay, so we have 2 possible scenarios in this particular case. Let's try a specific case. Our specific case is going to be xenon tetrafluoride. Draw the electron orbital diagram showing the hybridization. So I want you to draw the Lewis structure for this and see if you can correctly fill the hybridized orbitals. Try to draw the diagram correctly. I will reveal the answer after an awkward pause. So if you need to, pause here so you can do the things and then try it. Okay, xenon tetrafluoride is square planar, so it has 2 lone pairs. They are going to be in the first 2 hybridized orbitals, and the rest will have 1 in each box. Note that these are the orbitals for the central atom, okay? All of these hybridization schemes are for the central atom, whatever it is. So when you're going to go about doing this, start with the ground state of the central atom, draw in the hybridized orbitals of the central atom, and you will have done your job. So in this case, xenon started with a full octet because it's a noble gas, and when we hybridized it, we pulled 2 of the d orbitals to make the sp3d2, because this was an octahedral geometry, and 2 of those spots are filled with lone pairs. All right, I think we have a good idea of how to do the things. Let's summarize. All right, so the basic assumptions we made for hybridization. Hybrid orbitals form in covalently bound atoms. Hybrid orbitals have different shapes and configurations than atomic orbitals on isolated atoms. Hybrid orbitals are created by combining atomic orbitals, and the number of hybrid orbitals created in the set is equal to the number of atomic orbitals that were combined to make that set. All hybrid orbitals have equivalent shape and energy, and that shape is more or less like a P, but an offsides P, right, with a really big lobe on one side and a very small one on the other. The type of hybrid orbitals in the molecule depend on the electron geometry predicted by via CPR. And finally, hybrid orbitals overlap to form sigma bonds, and unhybridized orbitals form pi bonds. So, due to that point number 6, you fill the hybrid orbitals with 1 electron if they are bonding and 2 if they are lone pairs. You will have stuff in the p if there is a pi bond. So hopefully all of that made perfect sense, and you're going to rock it when we get to class.